In a lab outside Shanghai, engineers are showing off a piece of white fabric that has been dragged through mud, soaked in coffee, and rubbed with grease. And it looks exactly the same as it did before any of that happened. Not because someone cleaned it, because nothing stuck to it in the first place. This is not a stain-resistant spray you buy at the store and reapply every few washes. This is a fabric built at the molecular level to reject liquid and dirt entirely, permanently, without needing any coating that wears off over time. Western textile labs have chased this idea for decades and kept running into the same wall. Chinese researchers just broke through it, and what they built could change everything from hospital gowns to military uniforms to the shirt you are wearing right now. If you like videos like this, please hit the like button, because these take a ton of work to put together, and subscribe so you do not miss the next one. What you are about to see looks less like fabric and more like a material that has learned to defend itself. And by the end of this video, you will understand exactly why textile engineers around the world are paying very close attention. A shirt that laughs at coffee spills, picture a demonstration room. A researcher holds up a plain white shirt, no different in appearance from anything hanging in a closet anywhere in the world. Then they pour a full cup of coffee directly onto the chest. Instead of soaking in and leaving a brown stain, the liquid beads up into a perfect sphere, sitting on the surface of the fabric like a marble resting on glass, then rolls straight off onto the floor without leaving a single trace behind. They repeat it with red wine. Same result. Motor oil? Same result. Ketchup, mud, ink. Every single time, the liquid refuses to make contact with the fibers themselves, gathering into a droplet and sliding away. This is not a party trick using a special demo fabric treated just for the camera. Researchers have run the same shirt through hundreds of repeated stain tests, and the effect does not fade. That detail alone separates this from anything currently sold as stain-resistant clothing. The waterproof sprays and coatings used in outdoor gear today work by adding a thin chemical layer on top of normal fabric fibers. That layer repels water reasonably well when it is brand new, but every wash cycle strips a little more of it away. After 20 or 30 washes, most stain-resistant clothing performs barely better than a normal shirt. The new Chinese fabric does not use a surface coating at all. The repellent property is built into the structure of the fiber itself, which means washing it, wearing it, and stretching it does not wear the effect away because there is no separate layer sitting on top to wear away in the first place. Copying a leaf that never gets wet. To understand how this actually works, you need to look at something that has existed in nature for millions of years, the lotus leaf. If you have ever seen water roll off a lotus leaf in perfect little balls, you have already seen the exact physics this fabric is built around. Scientists call it the lotus effect, and it comes down to surface texture at a scale far too small for the human eye to see. Under a microscope, a lotus leaf is not smooth. It is covered in millions of tiny bumps, each one coated in a layer of natural wax. When a water droplet lands on that surface, it cannot spread out and soak in because it only ever touches the very tips of those microscopic bumps. Almost the entire droplet sits suspended on a cushion of trapped air between the bumps, so surface tension pulls the water into a tight ball instead of letting it spread. Add any tilt to the leaf at all, even a few degrees, and that ball simply rolls away, picking up dust and dirt particles along the way like a tiny rolling magnet, leaving the leaf cleaner than before the rain even started. Chinese materials scientists spent years figuring out how to recreate that exact microscopic bump structure. Not on a leaf, but on individual textile fibers thinner than a human hair. Using a process that manipulates fibers at the nanometer scale, smaller than a virus, they etched a similar bumpy texture directly into the fiber surface before weaving it into fabric. Layered on top of that structural texture is a specialized molecular coating, one that bonds directly into the fiber material rather than sitting on top of it, giving the surface an extremely low affinity for both water and oil at the same time. Most repellent coatings only handle one or the other well. Getting a single fiber to reject both water-based and oil-based liquids equally, permanently, is the specific breakthrough that had stalled Western labs for years. Why oil was the real problem? Making a fabric repel water is honestly not new. Cheap sprays have done a reasonable job of that for decades. The much harder problem, the one that stopped nearly every serious attempt at a truly self-cleaning fabric, is oil. Oil has a much lower surface tension than water, which means it wants to spread out flat and soak into fibers instead of forming a neat bead the way water does. A texture built to repel water often does almost nothing against oil. It slides right past the microscopic bumps and soaks straight into the material underneath. To solve this, researchers had to design a fiber surface with two different defense mechanisms working at the same time. The nanoscale bump structure handles the physical side, keeping any liquid from making full contact with the fiber. But layered into that structure is a fluorine-based molecular chain, arranged in a way that dramatically lowers what scientists call the surface energy of the fiber. Low surface energy means liquids, oil included, simply do not want to spread across the material. They would rather hold their own shape than stretch out and cling to the fibers. Combine the physical bump texture with this chemical low-energy surface, and you get a fiber that treats oil the same way it treats water, as something to be rejected and rolled away, not absorbed. Getting both effects to work together at the nanometer scale, and getting that combination to survive being woven into thread, stitched into clothing, and worn through ordinary daily abuse, is where years of failed attempts by labs in Europe, Japan, and the United States hit a wall. Most could get one property to hold up under real-world wear. Very few could get both to survive at once. A team of German textile chemists who reviewed early published data on this fiber reportedly described the dual mechanism approach as solving two separate, multi-decade research problems inside the same material, something they had not seen achieved simultaneously before. Building it into thread, not spraying it onto cloth. The manufacturing process matters just as much as the chemistry. Instead of weaving normal cotton or polyester thread and then dipping the finished fabric into a repellent bath, engineers treat the raw fiber before it ever becomes thread. Each individual filament goes through the nanoscale texturing process first, then gets bonded with the low surface energy coating at the fiber level. And only after that does it get spun into yarn and woven into fabric. This order of operations is the entire reason the effect survives washing. A coating sprayed onto finished fabric sits on the outer surface of the weave, exposed to friction from every wash, cycle, every fold, every time the fabric rubs against itself in a dryer. A property built into the fiber itself is protected inside the structure of the thread from the very beginning, distributed evenly through the material rather than sitting as a vulnerable outer layer. Washing does not strip it away because there is nothing sitting on the surface to strip. The repellency is a property of the fiber, the same way the color of a dyed thread runs all the way through rather than just coating the outside. Manufacturers involved in early production runs say the treated fiber can be spun and woven, using largely the same industrial equipment already used for normal synthetic fabric production, with modifications to temperature and tension settings to avoid damaging the microscopic surface texture during the weaving process. That detail matters enormously for scaling this up. A material that requires building entirely new factories from scratch stays a lab curiosity for years. A material that can move through existing textile manufacturing infrastructure with modest adjustments can reach mass production far faster. Where this actually gets used first, the most obvious application is everyday clothing, and Chinese sportswear and outdoor brands have already begun incorporating early versions of the fabric into limited product lines, marketed around the coffee spill and mud demonstrations that have circulated in trade publications and industry showcases. But the more serious applications sit outside of fashion entirely. Hospitals represent one of the most immediate use cases. Medical staff uniforms and surgical gowns currently absorb blood, bodily fluids, and other biological material during procedures, creating both a hygiene risk and a constant laundry burden for large hospital systems. A fabric that liquids simply roll off of, rather than soak into, could reduce contamination risk for staff and cut down dramatically on how often certain garments need replacing due to permanent staining. Early trial partnerships between the research team and several Chinese hospital networks are reportedly already underway, testing the fabric in high-exposure environments like operating rooms and emergency departments. Military and industrial applications follow a similar logic. Uniforms exposed to fuel, oil, and chemical residue in industrial or field settings currently need frequent replacement once repellent coatings wear down, which is expensive at scale and creates supply chain demands in situations where resupply is difficult. A fiber-level repellent that does not degrade with wear and washing solves a genuine logistics problem, not just a convenience one. There is also an environmental angle that researchers have pointed to directly. Traditional stain-resistant treatments often rely on PFAS chemicals, the so-called forever chemicals that have drawn increasing regulatory scrutiny worldwide for their persistence in the environment and links to health concerns. Because this fabric achieves its effect primarily through physical nanostructure, combined with a more targeted, lower concentration chemical treatment, rather than a heavy PFAS-based coating, early lab data suggests a meaningfully smaller environmental footprint than older generation stain-resistant textiles, something regulators in Europe and North America have been pushing the entire textile industry toward for years. The limits nobody is hiding. It is worth being clear about where this technology currently stands, because the researchers themselves have not claimed it is a finished, universal fabric. The nanoscale texturing process is more expensive per meter of fabric than standard textile manufacturing, which means early products carry a noticeable price premium over ordinary clothing. Extreme abrasion, the kind of aggressive repeated scraping you would get from heavy manual labor over years, can eventually wear down the microscopic surface texture on the outermost fibers, though at a dramatically slower rate than a sprayed-on coating would degrade. And the fabric currently performs best in woven synthetic blends with cotton and other natural fiber versions still undergoing refinement to achieve the same durability. None of that erases what has been demonstrated. It simply means mass adoption across every category of clothing will take further engineering work and cost reduction before it reaches the average shopper the way normal water-resistant jackets did over the past 20 years. A small fiber with a big ripple effect stepped back from the coffee spill demonstrations and the microscope images, and what this fabric really represents is a solved problem that global materials science has circled around for decades without closing. Getting a single material to durably reject both water and oil at the fiber level, without a coating that wears away, touches an enormous range of industries at once. Healthcare, defense, industrial safety, consumer fashion, and environmental regulation, all pulling on the same underlying breakthrough. Textile manufacturing has historically been one of those industries where progress moves slowly. Incremental improvements to dyes, weaves, and coatings stacked up over generations. A shift at the fiber level, changing the fundamental physical behavior of the thread itself, rather than adding another surface treatment, is the kind of change that does not happen often. When it does happen, it tends to ripple outward into product categories nobody initially expects. The same way waterproof breathable fabrics eventually showed up in everything from hiking boots to tents to car interiors after their initial development decades ago. For now, this fabric exists in limited product runs, hospital trials, and industry showcases, not yet on the shelves of every clothing store worldwide. But the underlying science has been demonstrated, repeated, and verified by outside labs reviewing the published research, which is usually the hardest hurdle for any claimed materials breakthrough to clear. The next few years will determine how fast it scales. But the wall that stopped Western textile science for decades has been broken, and it happened in a lab outside Shanghai. If this deep dive into fabric that refuses to get dirty surprised you, hit that like button, subscribe, and turn on notifications so you never miss the next one. There are more videos on the screen right now if you want to keep exploring. So here's my question for you. Would you pay extra for clothing that never stains? And what would be the first thing you would want made from a fabric like this? Draw your answer in the comments below.